Introduced in year 11. In year 12, we had competitions on titration. Year 1, we started using all these to prepare solutions. And year 2, we'll put you in real life situation. 1 year, I went to the hospital. I saw that bag. You know, we usually have the saline solution. When you get sick and the doctor basically inject. You know the description that was written on the bottle, I took the picture and I gave that picture as an examination question. And surprisingly, that year, that question was badly done. Nobody knew what was it. It was written 0.9% weight by weight NaCl. And I asked them to convert that into molarity. As a chemist, if you don't know what is written on the case there, which is our work, because that's percentage of NaCl in terms of weight by weight, if a chemist can't study that, then how can you expect them to be knowing it? Tell me. You know, once I went to the hospital with my dad, the intern came, you know the way they acted? That is, they are God. They showed me the data and it was in ppm. And he told us, you don't understand it. He said, you don't understand it, so don't worry about it. But it was an important fact, because based on that we decided to know whether my dad will undergo operation or not. Because there was a PSA count that was related to prostate cancer. And he said, you people don't need to know it. Why? Because he didn't know. So I explained, come. I said, I tell you what it means. It means parts per million. He said, are you a chemist? That's the time, you know. So, being a chemist, make sure you know all this stuff, right? So that you know why we are basically preparing this solution. So 0.9% weight by weight, what does it mean? In every 100 grams of the water or solution, 0.9 grams is NaCl. That is why 0.9 over 100 times 100 over 9, what becomes 0.9%? That means in 100 grams of water, you are adding
0.9 grams NaCl.
So that's how you get 2.9%. So, molarity, moles of solid over volume of solution. Always remember the volumetric flux. Molarity, moles of solid over kg of solvent. That means we are not taking into account in this one the mass of the or the volume of the solute. It's just solvent. Mass percent, this is exactly what I said, 0.9 over 100. So mass percent means the mass of the solute over the total. And if you multiply this by 100, it becomes percentage. If you don't multiply by 100, it remains a fraction. Parts per million, ppm, is same as milligrams of solute over kg of total mass. If you look from the gram side, gram, if you go to kg, you have to divide by 1000. From gram, if you go to milligram, you have to multiply by 1000. The difference between the two is 6, 10 to the power 6, 3 this side, 3 this side. So anything raised to the power 10 to the power 6 is parts per million. Milligram per kg. So if you are looking at the gram, you have to go to milligram, you multiply by 1000, and from gram if you go down to kg, you divide by 1000. So the difference between the two is times 10 to the power 6. That's what it means, parts per million. And mole fraction. We use chemistry here, we use the word molar. If I say the fraction of female in this class, it would be number of females over the total student. But when I use chemistry, I will say moles. There's nothing chemistry there, it's all maths. Fraction plus fraction is equal to 1. If you go to the chemistry lab, or any lab for instance, and you ask them to give you 1 molar HCl, then you expect the technician to go to the the chemical stores, get the concentrated HCl, bring it to the lab, dilute it and give it to you the next day. Why? Because if you add acid to water, what will happen? Heat will be released. It's an exothermic reaction. When you dilute acid with water, it's an exothermic reaction. A lot of heat will be released and the volume will tend to be high. As the solution cools down, your total volume will become less and less and less. That's why we have to use C1, V1 is equal to C2, V2. Then V2 is not always the right one when you are mixing. So you have to give a 12-hour break while the solution cools completely to room temperature, then you make it up. If you come to do the lab, you ask 1 molar, you get the bottle from the lab, and this is what it will be written there. 35% purity, weight by weight. Write it down. 35% purity, weight by weight. Let me check. There you go. Okay. Write this down. Hydrochloric acid, 36.5 to 38%. We'll take it 38%. Weight by weight. And the density is given to be 1.19. 1.19 gram per cm cubed. Right? So we are looking at 38% weight by weight HCl purity, and the density is given to be 1.19 gram per cm cubed. Calculate the molarity of HCl. Calculate the molarity of HCl with that information. This is basically what you will see in the chemistry lab. When you go in there, this is the bottle with that information. It's not in molarity. So your job is to now convert the data into molarity. Do it. You know how to approach it? This is what it means. 88% weight by weight means in every 100 grams of HCl solution you take, 88 grams is HCl. So if you know the mass of HCl, if you divide by the MR of HCl, you will get the moles of HCl. And then 100 grams, we have to change into volume. So therefore you use that formula, density is equal to mass over volume. If you know the density, you know the mass, which is 100 grams, you can convert that to volume in centimeter cube. Then change it to liters. So moles of sodium HCl over volume of HCl in liters gives you the molarity. So next week when you come to the lab to do the experiment on, sorry, not next week, week after next, when you come to do the experiment on adsorption, we'll give you the bottle of acetic acid. You do the dilution and do the calculation. The technician will not prepare the solution for you. Okay? Okay, let's move on. You know the calculation that I just gave you for HCl. If a second year student of USP can't do it, year 11 of any other universities around the world will be able to do it. Where is the problem? Student or system? Student. Because as soon as they see a little bit of math calculation or hard, it's not my area. Somebody else will do it for me. So make sure this is your bread and butter. Eh? All chemicals that you receive is not in molarity. It's recorded in weight by weight or volume by weight. So you need to understand what it means and then do the calculation. Chemical potentials. Do you understand this part? Free energy is a function of temperature, pressure and the different components we have in a system. Right? If I want to see how does one component in the system contribute to the end potential, what should I do? Keep all other components. Does that formula make sense here? Does that make sense here? I am looking at the change in G, differentiating T and keeping all other plus. I will see the change in G with respect to P, all other constant. Change in G with respect to the constant, all other constants. So if I want to see the potential of you today in the class, rather than the potential of the class, then I will have to separate the pressure, the temperature, and all other students except you. That's what it means. Get it? Then if I go back to another student, all other students will be constant except you. So, if I pick up 3 or 4 students from the class, and if I know the potential of 1, 2, 3 or the 5 students in the group, combined one will give me the total potential of that group. Clear? Understood? So if I have a mixture of water, ethanol, salt, whatever, if I want to know the total potential of the solution, I need to see the contribution the salt is making, The water is making, the alcohol is making, all the conditions, isn't it? So in order to know for the water, I have to keep all other constant. Does that make sense now? So if you are looking at only one component, does this word suit? Partial. If I had only one person in the class, will the partial be there? No. Molar. So if I am only looking at water, I will find the molar potential of water. If I am only looking at the ethanol, then I am going to look at the molar free energy of ethanol. But if I mix the two together in different proportion, then it becomes partial. Understood? Understood?
Yes.
So where can we see this? A very common one is in the student. When they come to university single, they need molar free energy. Full contribution towards the study. Yeah? The moment they will become partial, then the contribution becomes a bit less because some percentage is to go that side, isn't it? If you have two, then it becomes more problematic. Potential becomes less towards the study. That's what it means. So in the experiment, what we are going to do is to show you the effect of molar free energy in solutions which are miscible. Immiscible will be separated. Miscible is when you change the potential of the other one. I think I did explain. If you want to just take the picture, but it will come on your lecture recording. Okay. So in order to check this part, we have got an ideal solution and a non-ideal solution. In an ideal solution, what happens? All the interactions are, this is the problem. I said ideal solution, they said no interaction. I didn't say ideal case. Eh? Ideal solution, all interactions are same. Non-ideal solution, interactions are
Different.
So, if I take water, all the interactions in water are same. Ideal or non-ideal? Ideal. If I take ethanol, all interactions are
Same.
same. Ideal, non-ideal?
Ideal.
If I mix water and ethanol, then
Not ideal.
why? Because you will have water interaction, ethanol interaction, water ethanol interaction. Get it? So all the interactions here become different. So the potential basically changes. And that potential will change according to the amount of one substance with respect to the other. If you have more of A, the influence will be more of A. If you have more of B, the influence will be more of B. You know, if you understand all the theoretical background, you could predict that if I mix these two together, what kind of property you might get. And if you can do that, then you become artificial intelligence. Without doing the experiment, you can predict. And that's what people are doing now. They have done so many experiments, and it's all lying here and there. So what they do in the artificial intelligence, go and bring in all the data together, and then they try to write a program, and from there you should be able to predict that if these are the conditions, then what will you expect. Clear? Then you go to the doctor, headache, Panadol. So what will be the dose? It will depend on your age. So if I make an artificial doctor, you just put in your name, your age, your weight, symptom, Panadol. But what the artificial intelligence will do according to your body weight, will tell you how many tablets you have to take within the time frame. Okay, so when we talk about non-ideal or real solution, for ideal solution, because the interactions are same, so 1 plus 1 will become 2. If you have real solution, then because one of them will interact, 1 plus 1 will not be 2. It will be less. Because when interactions occur, they bring molecules closer together, isn't it? So the volume will shrink. So 1 plus 1 will not be 2, it will be less than 2. Understood so far? Yes?
Yes.
So the question now is, if you come to my place and I give you a welcome drink, 1 full glass of water with 1 pinch of alcohol, what will be the effect? Nothing. Why? Because the potential of water will be. Yes? If I start to increase the concentration or the amount of alcohol, then what will happen? The potential will change. Right? What you might notice is that if I take 10 ml of water and 10 ml of alcohol, it doesn't become 20 ml. It might go very less. So you don't have to make it to the mark and say this should be 20 ml. 10 plus 10 there will be less than this. Why? Because some of the molecules will undergo interaction. So, the water and the alcohol in that mixture is no longer behaving like water and alcohol pure. Clear? That's why we call it partial molar, or partial volume of water and partial volume of alcohol. And that partial volume will depend on the amount of water and alcohol you have in the mixture. Understood? You know, sometimes when you go to the bar, when you say I want alcohol, so the barman takes the water, puts it into the glass, right? And then they one tops it up and never become 20 ml, less than that. Was he right or was he stealing? He's right there. Because the volumes are not additive. It becomes less. So you don't top it up. If you want 20 ml, then you should know the partial volume of water plus the partial volume of alcohol that you have to add, that will make it 20. It can't be 10 plus 10. Because they don't add up. Why? Because of the interaction taking place. And that's what I'm going to teach you, how to calculate that partial volume. Clear? Okay, so this is the formula. Moles of liquid 1, moles of liquid 2. Partial molar volume of liquid 1, partial molar volume of liquid 2. The question may be in your mind, how do I know the partial? Yeah, that's a very big and good question, we don't know. We actually have to draw the graph in order to get it. Because as soon as you add liquid, alcohol to water, you might see there is a change and then go back and do the calculation. That's how they form the table. So alcohol water is done, ethanol water done, methanol water done. These easy ones are done. If you go and look at those hard ones, those specific ones, people might not have done it. And that's where the research gap is, because no one knows the answer to it. When one of you take and say, I want to find the phase diagram for the partial molar volume for the different liquids, the different fraction, then you will just find. And if your data comes out well, if you think this is correct, send it for publication, then the whole world will see your result and use that as a reference material later on. Clear? So in this case, if I have 5 moles of water and 3 moles of ethanol, the volume that I am looking at is the total volume of the solution. Right? If I divide N1 by N1 plus N2, I will get mole fraction of V1. That's how I get it here. If I take N2 divided by N1 plus N2, I get mole fraction of V2. So mole fraction multiplied by the partial molar volume of liquid 1 plus mole fraction times the partial molar volume of liquid 2, you add them up. This volume is for 1 mole of the solution. 1 mole of the solution, not the total moles. Total moles are here, 1 mole is. What is the volume of 1 mole of water? Huh? 1 mole of water, what volume? Mass of 1 mole of water? One mole of water, what is the mass? 19 grams per mole. And if density is 1, then 1 mole of water will have what volume? 18 cm cube. Right? This is what this part means, but this is for the mixture. You see the example. Suppose 54 grams of water, how many mole? 54 divided by 18 is mixed with 54 grams of ethanol. You need to know the MR of ethanol. So, if I know the volume of water for 54 grams and if I know the volume of ethanol for 54 grams, if I add them up, if it was a real solution, then it should add up to 123.06 additive. Right? Additive. But ethanol and water are not additive. Why? Because some interaction will take place. If it was 50 grams of water plus 54 grams of water, the volume that I get, you can add them up. Right? In this case, this many water plus this much is not going to be additive. It's not going to be 123.06. It will be less than this. Because some interaction will take place. And what we find here is that instead of having this volume, we get this. Right? So the partial molar volume of water is 17.3 and the partial volume of ethanol is 2. So the place where the formula I was showing V1 and V2, this is what goes in. And then your moles that you have calculated, 3 here and 1.73, it goes in according to their place. If you add them up, it gives you 118.74 rather than 123.06. Right? The question is, where did I get this from? So I will give you the table. Right? A graph like this. So you need to know how to read the graph. 3 moles of water, right? And 1.17 moles of ethanol, right? Here. 3 plus 1.173. That will give me total. So if I have to find the mole fraction of ethanol, it would be moles of ethanol over total mole. Right? So for the solution mixture that I was showing you, it comes to be around 0.3 mole fraction of ethanol. From here you drag one line up. It cuts here for ethanol, come across, this is the value. If you go up here, this is the one for water, it hits here, you get the partial molar volume of water for this mole fraction there. For this mole fraction, the ethanol is here. Okay? You know how to read it? Mole fraction, draw the line up and see where it cuts. So that becomes the mole fraction of ethanol and mole fraction of water for that fraction that you have in the mixture. Then you take it and apply it into that formula. So this graph basically helps you to get these two volumes here. Is it? In this number of moles. If the mole change, fraction will change, these values will change. Because if you say, for example, if the mole fraction becomes 0.4, then I will have to come to this point here, isn't it? Then draw one line up, cuts here, then you go and check that side, it goes up, cuts here, check here. Unfortunately, for your course, this is the only graph I have. So what I will do, if I have to give you the graph, I need all the small divisions there. So how can I do that? I'll have to go to the internet, get a green paper, copy this graph, paste it on the green paper and copy the whole thing. Then I'll get the green thing. And that will be part of grid there. So then it will be easy for you to read the grid. See, the internet is good for a lot of things, apart from social media. Yes or no? So when I say I'm going to take this cut paint and people start looking at me, I'm going to steal something. It's not that, you can use it. You're not stealing ideas, you're making a new fact there. So in general, if you have 1, 2, 3, 4 components added together, then the formula will change. V is equal to N1, V1 plus N2, V2 plus N3, V3 plus N, so on. Now basically this is what it means here, that the total volume change will depend on the number of different components we have added. Right? So how will you do it? If you get 3 components, how will you do it? You will check between these two first, then keep this one constant. Then you will check between this and this, keep this one constant. Then you will check between V2 and V3 and keep this one constant, right? Then from there you will know the volume that will be required by V1, volume required by V2, volume required by V3. Clear? If I have 3 liquids added together, then you will get the total change. You will be able to see the total change. But the question is, how much is 1 contributing, how much is 2 contributing, and how much is 3 contributing? So what you will do, you will press check with 1 and 2, keep 3 constant, don't add the third one. Then you will do 2 and 3, volume 2 and 3, but you will keep volume 1 constant. Then you find out how much does 1 contribute, 2 contribute, and then the final third one. And then once you know all that, get it out. Now, this is in partial molar volume. Right? I tell you another place where they were applying it, but it was in a totally different field. Week before last, I was down at one of the buildings and I met an electrician. And he was looking at the light and he couldn't go inside, but he had the switch. And he didn't know which light and which switch was going there. So when he turned on the switch, all the 3 lights went up. And he wanted to remove it and make one after one. So he was not sure whether the power was coming from the switch to that light and this light was supporting it here and so in series, or was it in parallel from different places? So what did he do? He removed the power from there, then he turned on the light. Get it? He removed the power from the first light and then he turned on the switch. If this two turns on, that means the power is coming from somewhere else. Isn't it like this? Isn't the concept is like this? So if the power was still coming in, that means this is not supporting the power there, isn't it? That means the power is coming from somewhere else. So remove number 2, get back number 1. Turn on again. If it still lights on, that means all the powers are coming from different sources separately. Only the switch is one. That's what it means or not? So when you look at all this situation, you just have to look from that concept and then just apply it. Here I am using chemistry, so I have to put solution. If I was an engineer, I would have put material. But the concept remains same. Okay. Rolls law. Don't write it now. You write Dalton's law first. Don't write this law. You write Dalton's law first. So Dalton's law is P total is equals to
P1 plus P2.
PA plus
PB.
PB. Where you have PA, you drag one arrow and write this. P total is equal to PA plus PB. Where you written PA, draw one arrow down and write that. That PA is equal to this part here. And that PB is equal to this part there. Understand?
Yes.
Now you should be able to go and do question number 10 in tutorial sheet 1. That you had the flow, I told you hold on, this is the one. So what it means is this, that the partial pressure of the gas is equals to the pure pressure multiplied by the fraction. It says the partial pressure of any component I is the product of its vapor pressure in the pure state multiplied by its mole fraction in the mixture. I want to confuse you a little bit so that you go home over the weekend and then you will study. If I tell you now here, then what you will do is go home and relax. I want to confuse you. So then when you go home, then you figure out what is the right way to do this part. Imagine you have a beaker Inside the beaker, you have two liquids in different amounts. You have two liquids in different amounts. Right? Can you find the fraction of each liquid? Yes or no? You have in a beaker two liquids of different volume. Different volume. Can you find the fraction of volume 1 and liquid 1 and liquid 2? Now, I have 10 ml of liquid A and 10 ml of liquid B. Can I find the mole fraction of A and B?
Yes.
Yes, eh? So if I divide by the MR and divide by the MR, I will get the moles. Then moles of A over moles of A plus B will give me the moles of A in the liquid, and B over A plus B will be the mole ratio of B in the liquid. Then over time, A and B will vaporize and come into the vapor phase. Right? Here you see A is in the pure state, B is in the pure state. Then they go in the mixture to give you the partial pressure. My question is this Xi, is it the one in the mixture or sorry in the gas mixture or in the liquid mixture? Okay, that's my question. I have a beaker, I have two liquids in different amount. The two liquids vaporize, get into the vapor phase. In that vapor phase, you have A and B. I can find the partial pressure of A using that formula. I can find the partial pressure of B in that vapor phase using that formula. But the question is, where do I get the X1 from? In the gas phase or the one in the liquid phase? That's your homework. Okay? I had written it here, but I removed it. Because you know why I can just take pictures so you don't do any work at home. If you go home and start looking for it, then you will realize, okay, this is important. This is how you do it. Is my question clear? X1 from where? Yes or solution? Where will you find the answer? You type this question in the internet, and it will give you different possible solutions for Rolle's law. Then read the solution and make out from there where the X1 is coming from. So basically, Dalton's law coming down to Rolle's law. You do the homework, then I will go further on from here to explain things on Monday. Okay? Before you go, I just explain a little bit on colligative properties, because my time here is important to find. Our one lecture topic, I'll just explain it in 3 minutes. Right? It's a one lecture topic. If you read, it takes you one lecture, then 50 minutes, but I'll explain it in 3 minutes. Listen carefully. You have a beaker, right? Inside the beaker, you have a liquid. If you start heating the liquid, what will happen? The liquid will go into it, vapor phase. When the vapor phase equals the atmospheric pressure, it will start.
boiling.
If I add salt to the water, what will the salt do? It will get dissolved, come to the top of the layer and block the liquid molecules from evaporating. So what does the salt do? It lowers the
Boiling point.
vapor pressure. Isn't it? If the vapor pressure goes down, you require less heat or more heat to boil.
Less.
Elevation in boiling point. If you add the salt, the boiling point goes up. That is why you add salt in the water at home to cook food. Because you don't heat the water at 100 degrees. You make it a bit higher. Clear? Now if the salt is present in the liquid, can the liquid molecule come together and crystallize? No way. Why? Because the salt molecules are blocking it. So what do you need to do? You have to cool it. Oh. Depression is freezing. Those are the three properties for polymer. If I start going through this, it will have one whole lecture. Okay? Right? So I've just explained the whole thing in correlative property. What does it do? Before, when we didn't have instrument, people used to know how much salt have I added to the liquid. And because of the depression in all these properties, they were able to calculate the molecular weight of the solid. Okay? So whatever I just said about colligative properties will be part of your text, which I will cover on. Have a nice weekend and please don't get sick.